So if you haven't already, please open the next notebook in the drive. And this is about linear algebra. And so the idea is, in the real world, we collect numbers as our data. And linear algebra is all about how do we work with lists of numbers, right? So the simplest model that we're talking about, so machine learning model that you can have is a linear model. So y equals mx plus b. Remember, y equals f of x. So in this case, f is just mx plus b. So this is perfectly fine for when you have a single variable, x, as input, and you're trying to predict a single number as output, y. But when you have many inputs, like different sources of data that you're collecting, and you're trying to predict multiple numbers, then the simplest model that you can think of would be this linear model, y equals mx plus b, where m is some kind of linear transformation on your inputs. So what does that mean in terms of what we write in Python? Like, what does the data look like? So these matrices, M, are going to be square arrays. So they have a specific number, sorry, not square arrays, just arrays of numbers in general with 2 dimensions. They'll have some number of rows and some number of columns. So M by N is M rows, 2 columns. So this is a 2 by 2 matrix. And we'll represent each of the symbols inside of this matrix, this array of numbers, by its row and its column. Some special cases of matrices you might be interested in are column vectors. So for example, if you have m observations, you'll commonly organize this into an m by 1 array. So you can see this is a 3 by 1 matrix. And important fact, if you have 2 matrices that have the same dimensions, m and n, then you can add them together just by taking element-wise addition. So for Python, all these matrix operations are provided in a package called NumPy. And this just makes it easy to work with these arrays. So to define a matrix, we have to import these packages. So this makes the code in NumPy available to Python. And this is just a shorthand for, let's call this NumPy library NP. So we'll refer to this NumPy as NP. And this is for plotting. So the first function we need to think about is this np.matrix function. So NumPy has this function matrix. You can see it takes in a list of lists. And the important thing is that all the lists inside this bigger list have to be the same length, right? So I can take this list of lists and create a matrix out of it. So the 1, 1 entry would be this 1, 1, 2 entry would be 2, 2, 1, 2, 2. Similar to how list indices start at 0, the indexing for matrices is also starts at 0. So this is actually the 0, 0 entry, 0, 1 entry, 1, 0, 1, 1. Okay. So what are the columns of A? You kind of just read it off of this representation. You can see the first column is 1, 3, and the second column is 2, 4. So just a short exercise to check your understanding. Uncomment all of these lines. And I want you to make just an arbitrary matrix B here, such that we can add it to this A that we defined up here. So first, what should the shape of B be so that we can add it to A? Well, the easy line to complete is this one, where we're just adding the two. So NumPy makes it so that you can use this addition symbol between two matrices. And you see up here, we've defined a 2 by 2 matrix A. So here we need a 2 by 2 matrix B. So remember, we create a list of lists where the entries are some random numbers. You don't need these spaces, but it helps with readability. So this creates the matrix 45, 88, 45, 5. And you can see we just add it to A if it runs. Oh, sorry. So we've added the entries, 45 plus 1, 88 plus 2, 45 plus 3, 5 plus 4. And you get what you expect. All right, so with this syntax in mind, I want you to define this matrix, V, as a column matrix. So can anyone tell me why this is wrong if I write it like this? So the shape of this matrix is 1 row, 2 columns. So I actually need to write it like that so that it's 2 rows and 1 column. Okay. And this will be important later on, why we always represent column vectors as this type of matrix. There's a special matrix called the identity matrix, and we'll see why it's called that later. And it just has ones on the diagonal, and this one has to be square, which means it has to have the same number of rows and columns. So there's an identity matrix for every whole number. There's also this operation called the matrix transpose. And what it does is it flips the upper half of the matrix, so up here, and the bottom half of the matrix. And that's useful here. Why this was wrong before. Why this statement was wrong before, it wasn't the right shape. It was kind of flipped on its side. So the .t operator here transposes it so that it is the right shape. Oh. As you can see, we wrote it as a 1 by 2 matrix, but because we transposed it, it looks like this 2 by 1 matrix. All right. There's special matrices called symmetric matrices, and they have the same entries up here as their transpose. So 2, 2, You can 3, 3, 6, 6. These are the same numbers. Okay, and we've mentioned what, like a column of numbers we can call a vector. And vectors, they come from physics and math, where you have some kind of directional information that you want to encode. For example, north, south, east, west in the plane. And these vectors include the direction. The magnitude is computed as this formula here, which is called the magnitude or the norm. You use absolute value symbol. And so this square root of the sum of the squared entries, this kind of looks like the Pythagorean theorem if you just truncate the first two. And that's kind of the motivation. And if the magnitude of the vector is 1, then we call it a unit vector. So in NumPy, you actually have to go down a few libraries. So numpy.linalg.norm, this implements this function up here. And you can check this number, this norm, manually by just writing the square root of the sum of the squares. So you can see these agree perfectly. And now begins the list of different ways that you can combine vectors and matrices. So the first concept is the vector-vector dot product. So if you have two vectors, you can compute their dot product. And it's the sum of each of the entries multiplied by the other vector. And the point of this dot product is to tell us the similarity of the two vectors. Geometrically, it gives us something in terms of the cosine of the angle between them. But the interpretation is if the dot product is large, then the vectors are either aligned in the same direction or aligned oppositely. So you can use this formula, for example, to compute the angle between the x and y axes. So we expect this to be 90 degrees, or pi over 2 radians. And you can see if you rearrange this equation up here and take the arc cosine of the dot product, then you get roughly pi over 2. So dot product is a measurement of similarity of two vectors. The cross product is different. It's used a lot in physics. And it takes two vectors and computes a third vector, which is at a 90-degree angle to the plane of these two vectors, or orthogonal to these two vectors. And there's an easy way to do this in NumPy so that you don't have to do it manually. So in this exercise, I want you to verify that the cross product of the x and y unit vectors in 3D is the z unit vector. So I want you to define x hat here, y hat here, and then put something here to compute the cross product. So just as before, the x hat unit vector is 1, 0, 0, right? Because it has unit magnitude and it only points in the x direction, the first entry. And then the second entry corresponds to the y direction. And if we compute the cross product, indeed you get the z hat unit vector, 0, 0, 1. Sometimes you'll want to multiply the vector by a real number, which is usually called a scalar. And you just multiply each of the entries of the vector by that number. OK. Now we get to the most important multiplication for linear algebra, which is matrix multiplication. And it's defined in a really specific way to make computations easier later on. So matrix multiplication computes another matrix such that the ith row and jth column of that matrix is equal to the dot product of the ith row of the first with the jth column of the second. So it's a really specific product. Fortunately, we don't really have to worry about that when we're dealing in Python. Python will just do that for us. But this is the definition. And this satisfies a lot of nice properties. It's associative. So if you multiply three matrices together, A, B, and C, you can kind of group them however you want and perform these operations one by one. But in general, we can't reorder them, so it's non-commutative. This matrix transpose that we used earlier, when you transpose the product, it's the product of the transposes, but in opposite order. And you can prove that if you go through this and look at the definition. And then this identity matrix that we introduced earlier, if we multiply on the left or the right by the appropriate matrix, we don't change the matrix. So that's why it's called the identity matrix. It acts like the number 1 for matrices. And so this was just a silly thing where I just made random matrices A and B with these functions from NumPy. And matrix multiplication is expressed as this at symbol. So you didn't have to compute this yourself. You just let a computer do it. And then the special case of matrix-matrix multiplication is this matrix column vector multiplication. And this has a geometric interpretation. When you multiply a vector by this following matrix, it rotates that vector counterclockwise in the xy plane. So here I've made this matrix to rotate it by pi over 2 counterclockwise. And here I've made the column vector. This is another way to make it a column vector, and we'll go over this later. And you can see when I rotate it by 90 degrees in the counterclockwise direction, I go from this x hat to y hat. And you can see this is numerical error here. It's essentially 0. OK. So there's a difference between this multiplication symbol and the at symbol. The multiplication symbol, in this case, it performs what's called array broadcasting. It kind of expands V to have the same shape as M so that you multiply pairs of elements from both. So in general, that's not the same as this matrix multiplication that we defined. So that's just an important distinction to remember. And so we have a list of operations that you can perform in linear algebra. We've gone over matrix-matrix addition, scalar-vector multiplication, vector-vector dot product. We talked about the cross product, matrix-matrix multiplication, matrix-vector multiplication. So all of these are just, I like to think of them as computational tools rather than having any meaning on them on their own. So you'll see applications of these operations throughout machine learning. And so I think we'll finish this section by talking about what matrices can represent. So you might have seen, Facebook memes that look like this, right? And the question is, can we solve these types of equations systematically? So linear algebra gives us the way to solve these equations. So instead of apples, let's call those x. So each of these is an x. So there's 3 x's. There's 0 bananas and 0 coconuts. So 0y, 0z, and that gives us 30. So 30. So I've rewritten all 3 of these first equations over here. And kind of the subtlety is you just assume that these 2 are the same and these 2 are the same. Because that's how they try to trick you in the meme. Okay, so with that, if you look at these 3 equations, you can actually make a matrix vector multiplication equation out of this. So you have the matrix here, which are the coefficients, 3, 0, 0, 1, 2, 0, 0, 1, minus 1. And if you multiply that by the column vector x, y, z, you would get everything on the left side here. And you're setting it equal to everything on the right side. So matrices are a convenient way to express linear equations of, systems of linear equations. And there's an algorithm to take care of this for you. It's called Gaussian elimination or row reduction. In MATLAB, it's, I think, the matrix backslash the vector. In NumPy, you just use this np-linalg solve. So apparently the solution to this is apples are equal to 10, bananas are equal to 4, and coconuts are equal to 2. And so then this final line gives you 16. Okay. We will not go through the rest of this. You'll see applications of what's called principal component analysis this afternoon, I think. So we'll leave it there, and I think we'll take a 15-minute break right now.